Okay, so here's a ice chart problem. So we've got a balanced chemical equation that's at equilibrium, so hydrogen and bromine gas are in equilibrium with hydrogen bromide, and we're told Kc is 2 times 10 to the 6, which is large, right? So we're going to expect a large amount of products at equilibrium and very few reactants. And then what information we're given is we start off with a certain number of moles of HBr, 3.2 moles, and it's in a 12-liter vessel. And so this is a typical problem. So what's the concentration of everything at equilibrium? So probably the easiest way to start this is to convert everything to concentration. So let's go ahead and say, well, what's the molar concentration of HBr? That's the number of moles in the problem, 3.2, divided by the volume, 12 liters. So to get the concentration, we just need to divide one by the other, so that is 0.266, and we'll keep a guard digit, so the 7 on the end. Okay, so now we have this, we can go back and fill this in our ice chart, so let's just zoom back over. So our ice chart always has initial, a change, and an equilibrium. And in this problem here, the initial concentration was 0.2667 moles per liter. I'll leave the units up for now just to make it a little bit easier to follow. We didn't have any hydrogen or bromine, so clearly we know that the change is going to go ahead and be shifting HBr over to H2 and Br2. And the shift can't be in the other direction because we don't have any H2 and Br2 to use up. So that means that we're going to use up 2x of the HBr. And remember where the 2 comes from. The 2 comes from the coefficient here. So every time we use up 2 HBr's, we are going to go ahead and make a Br2 and an H2. And so at equilibrium, we can just sum those top two lines. So over here it's 0.2667 minus 2x, and on the other side there's really nothing much to do here. We started with 0, we just add the change, and that's our equilibrium concentrations. Now a lot of these problems are really similar, and so I like to set them up exactly the same way every time. And so underneath my ice chart I like to write the expression for K. K is the concentration of HBr at equilibrium squared over the concentration of hydrogen at equilibrium times by the concentration of bromine at equilibrium. Okay, we don't always have to write the equilibrium, the EQ, if we don't want to, but we should remember that we can't use any old values. Kc, we were given in the problems, 2.18 times 10 to the 6, so that's pretty big, and that's equal to HBr at equilibrium, that's this right here, so we can fill this out, so 0.266 minus 2x, we don't know what that is yet, we got to remember to square it, and on the bottom we've got hydrogen and bromine, and those are just equal to x. So at first sight this looks like a pretty nasty problem. We're trying to solve for x, and we know that both sides here are going to involve terms in x squareds if we multiply it out. And so this is a case where we can take a shortcut, and it only works because the right-hand side is a perfect square. And so if it wasn't a perfect square, this really wouldn't help at all. The left-hand side then is 1476. The right-hand side, well, notice the perfect square, so the top and the bottom is basically a square, and so that means square rooting it is really just a case of canceling out the squared sign. So the bottom, we didn't write x squared, but we wrote x times x, and we know that's equal to x squared. So we square root it, and we're left with x all by itself. So now we need to rearrange and solve for x, and so we can flip the x down here up to over here, and so that gives us 1476 x's, and the right-hand side then 0.2667 minus 2x. We want to get all the x's on one side and all the numbers on the other side, and so we can go ahead and we can flip this 2x all the way over here, so that gives us 1478x, and on the right hand side then we're left with lonely old 0.2667. And so to solve for x, we just need to divide both sides by 1478. And we probably only really have three significant figures here, right? And if we go ahead and we calculate this, we get 1.804 times 10 to the minus 4. Okay, so what's x? Well, if we look back in the bottom of our ice chart, we'll see that the hydrogen concentration at equilibrium is x, and actually also the bromine concentration at equilibrium. And so we can say that basically both of these are equal to x. And so remembering to put in our units, 1.8 times 10 to the minus 4, those are concentrations, so moles per liter. Okay, so we've calculated two of the three concentrations. So the third concentration we need is the concentration of HBr at equilibrium. And we know that that's equal to 0.2667 minus 2x. And if we go ahead and we throw in x and we double it and we subtract it away, we get 0.266 molar as our final concentration. So in these problems, right, so the question is, did we do it right? How do we know, right? We got some numbers at the end of the day. Do we really know that we actually solved for this and got it correct? Well, one thing we can do to check is we can substitute these back in. And so we've got now all three of these equilibrium concentrations. The equilibrium constant is 2.18 times 10 to the 6. And so what we can do, right, is we can take all three of these concentrations that we've just figured out, and we can check that it's equal to the equilibrium constant. So what's this give us? This gives us 0.266 squared over the value of x, basically squared, which was 1.80 times 10 to the 4. And you know what? That's the same for bromine, so I'm going to go ahead and square that. And if we did the problem right, then it should be equal to ditto, so 2.18 times 10 to the 6. And if we actually calculate this, what do we get? Well, if we calculate this, we actually get 2.18 times 10 to the 6. Actually, we were pretty good there. Now, quite often what you'll find is that this will be close, but not quite the same. And the reason is that we're going to accumulate round-off error after round-off error after round-off error in these problems. And so if we keep all the numbers in our calculator, we probably won't have to worry, but sometimes it's kind of hard. I would say if your K is within 10%, you probably did it correctly. Okay, let's try another problem.